Hello, class. This is Mr. Hart. In this podcast, we're going to continue talking about energy, and we're going to look at energy conservation and how it relates to spring energy. Okay, so we're going to add another set of equations and another set of concepts that we can use when we're talking about energy conservation. So let's just remind ourselves, first of all, what energy conservation is, or what the law of conservation of energy is. It basically says that energy cannot be created or destroyed, only transferred between forms. Okay, so whatever energy we start with has to be the energy we end with. So we want to relate this to the specific context of thinking about springs. Okay, so when we work with springs mathematically, we got to be able to describe a couple of the properties of springs. Okay, we haven't talked a whole lot about them in class, so we need to come up with some vocabulary and some things that we need to be able to quantify, okay, and describe about these springs. Okay. So some of these things include what we'll call the K value, and basically this describes how strong it is by how much it can compress or stretch given a certain amount of force. Think about like a spring for a trampoline. That's going to be a lot weaker than a spring for like your car, for example, right? There's these huge giant springs in your car. There's springs on trampolines. There's super tiny ones, in other cases. How weak or strong these springs are, we can describe using this K value, and we'll get to that in a second. Okay. There's also what we call the equilibrium point. Okay, this is when a spring's just sitting there. There's not a force applied to it. It's neither compressed or stretched. It's just sitting there. That's what we call the equilibrium point of a spring. Then if we start to compress the spring or stretch it, that's what we call the displacement. How far we move it past that equilibrium point is the spring displacement. Okay, so let me diagram this to make it a little bit easier to see. Okay, so let's say we have some mass that's hooked up to a spring, okay, and it just normally sits at this point, okay? So if we're labeling these, then this spring, how strong it is what we call the K value, right? How thick the spring is, basically just how strong our spring is. Then this line, right, describes the equilibrium point before we put a force on it, okay? That's our equilibrium position for this mass, okay? And then if we move the spring over a certain distance, okay, this difference between where the equilibrium was and where we are now is the displacement, okay? That difference between these positions. It's also what we'll call x, okay, mathematically. Just this movement, okay, that stretches or compresses the spring, okay? So, with all that information now, I think we can finally start describing about the energy of a spring, okay? So, when you compress a spring or stretch a spring, it wants to go back to its original position, right? Its equilibrium. That requires some form of work to be done, which means the spring can store energy. When you stretch that spring, it's storing energy, okay? So that's going to depend on how strong the spring is and how far we have stretched or compressed it, okay? That leads us to this equation right here, okay? The energy of a spring, okay, I'm going to write it like this with the subscript, okay? But the energy of a spring is equal to 1/2 times the K value, okay? This is usually given to you, times the displacement of the spring squared. Okay. Now you'll probably notice this has a very similar format to the kinetic energy equation, and if you ever take AP Physics, you'll kind of see why that is, but just make note of that. But we have our K value and our displacement. If we have those two things, we can figure out how much energy stored in this spring. Okay. So let's try an example problem. So let's say you have a K value of 75 newtons per meter. You have a displacement of 0.4 meters. How much energy is stored in the spring? Well, all you got to do is say, well, I know my equation is that the energy in the spring is 1/2 kx squared. That will be 1/2 times 75 newtons per meter times by 0.4 meters squared. Okay, notice again that will give you a Newton meter, which will be joules, so that's good. But we put that in our calculator. And we get the energy stored in that spring is equal to 6 joules. Okay, so not a whole lot. It's kind of a weak spring. But there you go. So now we know how much energy is stored in that spring just by knowing these parameters. Okay. Let's try another one just to make sure we got it down. Okay. 2 students load a 10 kilogram watermelon into a watermelon launcher. If the spring has a K value of 630 newtons per meter and the spring is compressed a distance of 0.25 meters, how much energy is stored in the spring? Okay. Well, same thing. We say energy of the spring equals 1/2 kx squared. Notice we don't need the mass of the watermelon to figure out how much energy is stored in the spring. Okay. But we plug in those values, so we get 630 newtons per meter, a distance of 0.25 meters, okay, squared. We plug that in to our calculator, and we get that the energy stored is 19.7 joules. Okay? So there you go. So if you know how much the spring is compressed and how strong it is, you can determine how much energy it has. Okay? So pretty straightforward, but now we got to go back and start thinking about energy conservation. How does this relate to energy conservation? Okay? Well, just like before when we were doing gravity and kinetic energy and all this stuff, we can use energy of springs in our problems now. Okay? And this brings out a really big idea which we'll call energy path independence. Okay? Big long phrase, but what it means is it doesn't matter what path a system takes. All that matters is your starting state and your final state in that system. Okay? Now that may not seem very powerful right now, but it's going to help us solve some really complex problems. Let me give you an example of why. Okay? Let's say you have a roller coaster and the cart goes down the ramp and it goes through a loop-de-loop and then it turns and goes all which places and then runs into a spring. Okay? That problem would be impossible to solve with kinematics. But if we're using energy, it doesn't matter that the roller coaster went through a loop-de-loop. It doesn't matter what happened to the cart. All we know is it started up here with some potential energy and it ended down here into a spring. That's all that matters to solve how much compression the spring will have. Okay? Anything in the middle doesn't matter. We don't need it to solve for these problems, which is a very powerful tool. Okay? So let's go back to our watermelon problem. Okay? So now instead of asking, how much energy does the spring have, now we're going to ask how high does the watermelon go? Now the question is, do we need to consider kinetic energy in this scenario? Because you'll put the watermelon in the launcher, the spring launches it up, right? And we're wondering how high this watermelon will go from it, okay? It moved in that process, so do we have to do this calculation of kinetic energy, gravitational to kinetic and kinetic to spring and all this stuff? We don't have to. Right? All we know is it started with spring energy and it ended with potential energy. Because we know that, that's all we need to solve this problem. So if we were doing this problem right here, what we would say is that the energy initial equals the energy final. Okay? We don't care if it was moving in the middle. All we know is that it started with all spring energy, 1/2 kx squared, and it ended with potential energy, mgh. Okay? So if we solve this problem now, right, we can ignore all the intermediate stuff. We just have to solve this. Well, we're solving for height. You get kx squared over 2mg equals the height that the watermelon goes. Okay? Sorry, I had to switch color there so you could see this. But all we're going to say is, well, we already know K is 630 newtons per meter. Okay? X is 0.25 meters squared over 2 times the mass of the watermelon is 10 kilograms times gravity is 9.8 meters per second squared. Right? So if we can solve all that, we'll get the height of the watermelon. And the numbers show this is probably going to be really small. But we put that all on our calculator. Don't forget the parentheses as always. And you should get that the height that goes is 0.2 meters up. Okay, so not a whole lot, but there we go. But we solved this problem using just some simple energy conservation. We didn't care about its movement in the middle. All we know and all we needed was that the fact that it started with spring energy and it ended with potential energy. That allowed us to solve this problem. Okay. Let's do another one. I hope you're starting to see how powerful this concept can be. Okay, a 7.5 kilogram mass is dropped from a height of 2.3 meters above a still 550 Newton meter spring. How far does the spring get compressed? Okay, so again, it's going to be moving in the middle, right? It's going to have kinetic energy as it falls, but the only thing that matters is it starts with potential and it ends with spring. So again, we'll say, all right, energy initial equals energy final. In this case, we started with mgh. We end with 1/2 kx squared, but this time we're solving for x. Okay? So we'll times by 2 and divide by k. We'll end up with x is equal to the square root of 2 mgh over k. Right? Just times by 2, divide by k, and square root the whole thing. Okay, now I'm not going to write down the numbers this time just for sake of space, but again, you'll just plug in everything we have. Okay, so square root of 2 times the mass, which is 7.5 kilograms, times 9.8 times 2.3 meters up, divided by 550, all square rooted. We get that it will compress the spring a distance of 0.78 meters. Okay, there we go. So again, super powerful just by knowing our starting and final states. If we can relate it to energy, we can solve for these properties. Okay, let's do one more just to make sure we got this down. Okay, a 1.2 kilogram wooden race car is loaded onto a spring starter. The spring has a K value of 65 newtons per meter and is displaced a distance of 0.25 meters. How fast does the race car start the race? Okay, so we have, a wall, a spring coming off of it, our little car gets connected, and it gets pushed back, right? And it's going to go launching in this direction. Okay, so in this case, we know the mass is 1.2 kilograms. K value is 65 newtons per meter, and the compression distance is 0.25 meters, and we're looking for the velocity, right? This exit velocity. So it starts with spring energy, and it goes into kinetic energy. So when we're writing our conservation, we say energy initial equals energy final. In this case, it started with spring, and it ends with kinetic. Okay, so fortunately the halves cancel out. We get kx squared equals mv squared. Okay, we'll divide by m on both sides. We get v squared equals kx squared over m, and then we square root both sides, and we end up with this. So the velocity will be equal to the square root of kx squared over m. Okay. In this case, that's going to be K is 65 newtons per meter. X is 0.25 meters. Sorry, my handwriting's kind of small. And then over 1.2 kilograms. When we get our calculator and we calculate that, square root of 65 times 0.25 squared all over 1.2. We get the velocity of the car is 1.84 meters per second. Okay, and there we go. So again, I hope you see just how powerful this property is, this conservation of energy. If we can describe how energy moves, we can describe any of these other physical properties that matter to us. Okay, how much the spring gets compressed, how high the object goes, how fast it's moving. It all comes from just keeping energy conserved. Okay, so it's super powerful. But go ahead and do the homework. It's just on the same type of stuff, spring energy and conservation. Hopefully this all made sense. Let me know if you have any questions, and thank you for watching.